This conference will now be recorded.
Wonderful. So welcome everyone. Today we have Alon Regev from Keysight. Alon is a system architect in hardware and software domain with expertise in wireless, wireline, data centers, time-sensitive networks, and many more things. So he has 30 years of industry experience and holds over 70 patents. Alon is the chair of the Avnu testability subgroup and a member of the working group in IEEE Avnu and 5G ACIA, including representing Keysight, the IEEE 15.8 work group. So Alon, let's get into today's presentation, which is about what was it? Remind me again.
We're going to look at how to measure a follower clock quality.
Wonderful. Wonderful. So does that mean like when you have like these the ordinary clock on
Exactly
or something? Wonderful.
Exactly.
Okay, let's get into it.
No, so if I just need someone to make me a presenter and I can begin sharing.
And make a presenter. You should be a presenter now.
I am. I can share.
Wonderful. Let's do it.
I've only got to find the right application. There's only 17 screens of applications. And in Murphy's Law, of course.
Yeah. Murphy's Law.
Okay. Can you guys see my screen now?
Not yet. Yes, we can see it.
Okay, so going to talk about monitoring and validating a follower clock accuracy. We're talking about ordinary clocks here. So at a high level, first of all, I want to introduce Keysight. Some people know Keysight, some people don't. But Keysight was split off from Agilent. Agilent was split off from HP. We trace back our roots to Hewlett-Packard that was founded in 1939 by Bill Hewlett and Dave Packard. We're still making test equipment. They started making test equipment. We view ourselves as continuing that tradition. It means a great place to also be able to not only make products, but do some research and learn a lot of different disciplines. So having said that, I'm going to introduce today's talk. First of all, PTP time synchronization requires every component to behave as specified. A failure or incorrect behavior at any level, doesn't matter whether it's the grandmaster, transparent, or boundary clock, or the ordinary clock, will lead to time errors. Conformance and performance validation at both the component level and the system level, part of the deployment, help ensure operation, but we really want to test things post-deployment by monitoring so that we can detect a failure. While most components can be tested independently, a PTP follower ordinary clock does not provide a standard way to measure its quality. And in this presentation, we'll look at different approaches to measuring the measure or monitor the PTP follower clock quality. And I think some of you have seen versions of this presentation before, but I'm covering a little bit more here, including what's being done in 1588 today. So what's the observability problem? So a GM, transparent clock, boundary clock, behavior can be observed. In a GM, if it gets its time from a GNSS satellite, we can get the time from the same satellite and compare it to its output, or we can get the time from an authoritative source or another reference and compare it to the GM's output. And TC, you can compare input to output. The follower has no output defined by 1588. There are some optional ways of doing it, but without any of the options, the follower is just a clock sink, not a source. So we're gonna look at how do we overcome to actually be able to measure the follower time. So I'm also going to talk about validation, different phases. We talked about device test. Device test typically test a single piece of hardware or software. It could be a process, a library, a you know a NIC, whatever it is, but it's tested at that level. It typically is tested to conform to standard as well as to perform under both ideal, which are what I call the perfect conditions, as well as the normal, which are the imperfect conditions, such as having some noise on the clock, having network load, etc. We take a look at the effects of network traffic, and we also take a look at the effects of security. Get your system test, we care about correct system level operation. Here, you might have, for example, an entire data center, and you want to know what the end-to-end clock quality is. And here we're focusing often on scalability and performance, as well as resiliency and security. And finally, we want to talk about runtime behavior. And move my windows here. We can move this out of the way. No, I want, okay, here, I've managed to minimize it. Anyways, this lets you ensure timing performance, and detect failures, and potentially detecting certain types of timing attacks, all on a running network, and hopefully using minimal resource to do this. And finally, in many cases, there are regulatory requirements that require us to record or to validate and or record the time. So what does measuring the follow clock quality mean? Typically, we start by trying to measure the time error. The time error is the difference in time between the time that the follower has versus the time that's available at some reference, typically the same reference that is the grandmaster. So the idea here is that we subtract the time at the follower from the reference time, we get a time error. And from this time error, we can derive many other measurements. And here we're talking about the time error being a representation of accuracy. Here we're going to talk about what are some of the things that we can measure. So typically, we talk about various things. We talk about resolution, accuracy, and precision. Resolution is basically just the smallest interval between readout updates. Really what that tells us is what's the smallest unit of time during which we can sample something. Accuracy is the error between the real and the measured value. In our case, we're measuring it using the mean time error. This is also what's known as the constant time error. Stability is looking at the mean deviation with respect to variables most common time. And precision is looking at the standard deviation of the time error from the mean value. So at a high level, here's an example of a clock that's relatively accurate and relatively stable. You see the reference frequency and the sample frequency being the same. Here you see something that's stable and inaccurate. Here you're seeing unstable and accurate, and finally both inaccurate and unstable. And unstable means we don't know if it's going to stable. And so one of the points here is, in order to measure clock quality, you have to do it over time. You cannot just use instantaneous measurements. You want to see how this does over various measurement intervals. Continuing on this, so let's say you have a measurement sample set. If you take the average of that gives you your basic frequency, and then if we plot a histogram of this, it lets us view this from two different perspectives. Typically, a point near the top of the histogram is typically the mean. Then if the difference between that mean and the absolute and the correct time is the accuracy. And then if we take a look at the first standard deviation, we have the precision. So, oops, I don't know why it took, okay. Okay, then time error and time interval error. So we want to talk about what these terms mean, but time interval error is really looking at changes in phase over time. And so we're measuring the phase error. So first of all, what is a time error? Time error is a measurement we've talked about, taken every 1,000 seconds, and what we're given is what's the error versus the absolute versus phase. So if we have a reference signal that's got a certain phase and a measuring that's got a different phase, and they can be that phase error can be in femtoseconds or it can be in megaseconds or years. It doesn't matter. The point here is how of the two are at an instant. And you can plot that over time to see how we vary. When we talk about time interval error, what we're doing is we're looking at an observation interval, and we're comparing the time taken for that observation interval in the reference signal versus basically going through the same number of I'll call it edges in a measured signal. And this measurement, of course, depends on the observation interval, which is defined as tau. And Ti is used to measure the dynamic time error. And we don't compare the absolute time to reference time, but just the error occurring during the interval. And there are a bunch of I'm going to skip through most of the slide. A lot of stuff I'm covering now has been covered in previous presentations, but there are many matrices defined, and there are various standards that define them. I'm going to focus today on MTI and TDEV, just at a high level. So MTI, or maximum time interval error, is really looking at within a defined observation window, what is the maximum time interval error that you can have. And the idea here is that you start with an observation window, and you start with the smallest observation window you can have, and you keep on going, and you go across all your samples. Then you go to the next highest. So in our case, we have a sampling interval of 5 seconds. We can start with an observation window of 5 seconds. Then we'll take and we'll move that window across the entire set of time and measure the error. Then we'll have a window that's 10 seconds and do the same thing, and then we'll plot that, and we'll plot the maximum time found across the set versus the observation window used. And the idea is, for example, for an observation windows with tau equal to 30, we sample it multiple times, and we find that the maximum time interval error at that observation window happens to be 8, and we see that at this point in the graph. Now we're going to change that observation window size and test how this works with every observation window in order to generate a plot. I don't have the plot here, but the idea is we can show how we behave as the observation window increases, and MTI is going to keep on increasing over time. It can over the observation, as the observation window keeps on increasing, the MTI cannot decrease. I'm going to talk about MTI and TDEV. Both of these measure wander at the clock's output, but one of the things to observe about wander is wander can be at an infinitely low frequency. We can filter out certain frequencies of wander, but we can never filter out all of wander, because by design, all we can do is implement a low pass filter that allows us to pass certain lower frequencies and filter higher frequencies, but we cannot filter out every possible frequency. MTI measures the peak-to-peak phase variation, and as I said before, we compare it. In the y-axis, we're showing the phase variation. In the x-axis, we're showing the observation interval, and as I said, also never increase. It never decreases, so it is a pessimistic indicator. TDEV, on the other hand, measures the stability in the rate of phase change. It is plotted against integration time, and you can see TDEV that decreases and then increases. And it really gives an idea of the behavior. And for any clock output, we typically have masks that define the expected behavior. In simple terms, what this means is the MTI defines the maximum phase excursion within an observation window, and TDEV measures the noise level of the clock source in a given observation window. And both of them depend on a time parameter, which is the observation window. And because the limits are expressed through masks that are specified into the variable observation window, and these are provided by various standards, mostly ITU standards. So now that I've ran through these, and a lot of this was repetition, but I'm going to dig into how we monitor PTP on a network. The first I want to discuss is why we monitor PTP on a network. The first goal is to make sure the timing performance is maintained. Even if we don't have any node failures, no GNSS interference, and no hacking, timing performance could degrade due to changes in network traffic patterns or even small changes in temperature. The second reason that we see commonly is just to build a data archive for regulatory compliance. There are many markets where monitoring the time accuracy, especially for timestamping purposes, is required, and monitoring is dictated. Finally, we want to use similar techniques to characterize a PTP implementation prior to using on a live network. Think of using in a subsection of your data center to validate that everything works, and wanting to characterize everything precisely prior to putting it live across all the data centers around the world. So approaches to monitoring. The first approach is to do this completely within the follower. And there's two general approaches here. The first approach is you just compare the input clock to the local clock. The second approach is you compare the input clock to a second or a third or a fourth input clock. The second general approach is you use an external monitor. The idea here is that the follower in some way shares its clock with an external monitor, and the monitor compares the time with the reference that it has. And the third general approach is to compare with peers. This is kind of a distributed approach. The idea is that each peer shares its clock with a set of peers. It can be as little as one peer or as many as several dozens. And these peers can compare their clocks to measure the time error. And I'll talk through each of these in the next slides. So the first one of these is clock quality monitoring directly in the follower. And you see in my drawing, I have a beautiful detective or inspector on the follower taking a look at the clock quality. The idea here is that it's a fairly simple approach, and there are two general behaviors as we've talked before. The first one is you just compare the input clock to the local clock. This is the simplest approach, but you cannot actually detect inaccuracies in the clock. You can only detect the dynamic behavior of the clock. And you also cannot distinguish between the input clock and the local clock in terms of stabilities. You cannot tell if the wonder is happening on your local clock or on the input clock. And also, this cannot detect many types of attacks like packet delay attacks. A better approach is to compare time from two different sources, but this requires additional clock connections to each follower and requires the follower to potentially be able to follow independently two different clocks, so it can compare the two. This is best if the different clocks use different network paths, different domains, or different protocols or medium, and it's relatively straightforward to do in a data center where in a clock switch architecture, different sessions tend to use a different path. If only a single network connection is used, then a clock issue or attack that affects, for example, a single path or a single switch could affect both the time sources. Second general approach is to use an external time monitor, and so the idea here is that the follower receives this clock and then sends its local clock out to the time monitor in some form. That can be using a 1 PPS output. It can be using PTP on another domain. It can be used using a different type of message. can just be PTP on a different network, etc. And the time monitoring device can be any device or process on the network that has the ability to measure the error between the follower time and the reference time. And the reference time can come from the GM, or it can come from any other authoritative clock source. Again, this works best if the network path from the leader to the follower is different from the path to the monitor. But you have to watch out because the paths themselves can introduce errors. The traditional approach to use an external time monitor is to use a 1 PPS output. And this works well, but it's not scalable. Another approach is to use a reverse sync where the follower sends its time to a monitoring device. And there are multiple approaches. I'm going to show some slides in this presentation. And Doug Arnold and I submitted a proposal to the 1588 working group to standardize this. And we'll talk about that. And the external monitor can monitor not just a follower, but at least in theory, it can monitor any PTP device, including a GM, a BC, or a TC, as well, of course, as an ordinary follower. The path to monitor, as I said, may limit accuracy. So in many cases, we find that the accuracy of the monitoring cannot be greater than the accuracy of the follower under normal conditions because it's using similar path. But if you have more monitors on the network that are close to the follower, in some cases, you can get better quality or better accuracy, I should say. Some reasons to use an external monitor. Number one is regulatory requirements. There are some requirements where the device is not allowed to monitor itself. You want some third party that's considered neutral to monitor the time. Number two is we've seen cases where self-reported performance data is erroneous. For example, if you have asymmetries in the PTP network or someone just chooses to want to make their implementation seem better or worse than it is. The PTP node itself could have implementation error that affects the self-reported data. And finally, this is useful for characterizing a device. So if a follower has the ability to send its data out, we have the ability to characterize externally and measure its performance. And this is useful in a lab, but it's also useful in the real network as you roll out different versions of software or changes to various behaviors. Finally, I want to talk about peer validation of time. So in some ways, you can say this is similar to using an external monitor, except that a peer is your external monitor. Each follower shares its local time with a set of peers, and this can be done using similar methods to the monitor. And it typically works best with a randomized set of peers rather than always using the same peers or using the nearest peers, and preferably where they're not all in the same network locations or path. And there are going to be some inaccuracies due to the monitoring path that also have to be balanced. But if you measure everything by your two closest peers, you're going to still have the inaccuracies incurred by the shared BCs or TCs or cables in your path. This does not require any specialized monitoring nodes, but it does add additional network traffic for the exchange of the time information between the followers. And there is a balance between the bandwidth usage and how quickly you can detect issues, as well as the resolution of the measurements. I'm going to jump into methods for external measurement of the follower clock. So the first method that we've discussed is just comparing a pulse per second or similar output. The second method is to use a 1588 ingress event method, which I'll discuss in a minute, where a follower clock reports its time error. This is similar to the self-measurement, except it's reporting its self-measurement to an external device. The 1588 egress event monitor, where the follower provides the PTP time of transmit of certain messages, and that can be compared. So the PTP follower can now send another PTP message towards a monitor and provide its local time at which that message was transmitted, and then that monitor device can detect the time the message was received and compare those. Finally, we're going to talk about the reverse sync method, where the follower sends something more similar to a sync message or other signal or similar signaling message to the monitor to validate the timing. And for device testing, it's recommended to implement at least one of the above methods, but implementing multiple methods allows cross validation. So for example, it is for those people who implement the reverse sync, we typically recommend that they implement, for example, a 1 pulse per second output as well, so we can compare one against the other. Or in some cases, we can compare a physical event happening, like the time that an LED turned on or something else. Doesn't have to be a dedicated 1 PPS output. This is something that I think most of us know how to do, but I'm going to cover it here for completeness, which is just using 2 PPS outputs to validate time. One of them comes from a reference and one of them comes from the follower. And the idea is we use traditionally we used an oscilloscope to monitor this, but today there are many NICs that actually have a GPIO that can act either as a 1 PPS input or output. So you typically have one of them acting as an output and the second one acting as an input and measuring the time of the incoming signal. You'd then take into account the length of the wire between the 1 PPS output and 1 PPS input, and after compensating for that, you can now measure the difference in time. This is a fairly low-cost way of measuring it. The advantage of this is that it's been used for many years, a known industry standard. You only need a supported NIC or an oscilloscope to do this, and of course, Keysight sells the oscilloscopes, but I prefer the NIC approach because they're easy to get and they're available. But of course, the oscilloscope will give you a potentially a higher precision. If you need the femtosecond precision, using an oscilloscope will often be a better technique. But in most cases, using a NIC is adequate. The shortcomings is that the 1 PPS itself is often imperfect. We see in many cases where there's a fixed offset or jitter for the 1 PPS output. For example, we often see cases where the 1 PPS itself is generated using a different clock than the PTP clock, causing it to do some kind of, I'll describe it as aliasing when it's transferring the information between the clocks. Second, there are some devices that just don't support having 1 PPS output, i.e. devices with mechanical constraints that prevent this. Think of this as devices that are very far away or that are very small, like a watch or an implantable device or whatever it is. Finally, the devices under test have to be relatively close together, and this is not practical for large-scale testing. For example, you cannot have a 1 PPS between every device in the data center. You can have a 1 PPS signal between dozens of devices, not millions of devices, practically speaking. Next, I'm going to talk the ingress method that's defined in IEEE standard 1588 2019 clause 16.11.4. The idea here is that the follower declares its area at the moment it's receiving a sync message. So when the follower receives a sync message, it records its local T2 time at the time it received it, and it knows the T1 time that the leader sent the time because the T1 time is inside the sync message or inside the follow-up message if two-step is used. And then the T1 and T2 are reported on a signaling message, or option the offset from the master is reported, and then either the leader or the monitor device can compute a time error. The principle here is fairly simple. It's the same principle that's done when a device monitors itself, except that now it's sending that information to another device. There are 2 TLVs defined in 1588 that propagate this information. The first one is slave RX sync timing data, in which you have the T1 and T2 time in the sync origin timestamp and the sync event ingress timestamp fields, and the total correction field provides the PTP residence time through the various devices along the path. The cumulative scaled rate offset is not directly used as part of the time error calculation, but it can be useful in determining the source of the error. So I'm highlighting here as well. The second version of this, or the second TLV is used if the calculation is done within the slave itself, in which case what we're transferring is the offset from the master, which is the actual error, the time error. The mean path delay provides the path delay used in calculating the time error, and the neighbor rate ratio provides the rate ratio computed at the receiver of the sink, and that again can be used to help identify the error or the source of the error. Pros and cons. The advantage of the ingress method is that the reporting can be done in band with 1588 TLVs or using any other method. It does not require any extra capability on the follower except having some memory to store this and supporting these TLVs or other messages.
Alon, I was going to ask whether existence of boundary clocks in the clock tree is going to be a problem under this method.
So in theory, no. In theory, this can be well. It definitely can. It can be propagated at least across transparent clocks, but as what's being reported is sent just as a well. This probably cannot be carried across a boundary clock, which is why I'm going to talk about the reverse sync in a minute, which tries to overcome that.
Got it.
Okay. So the shortcomings, yeah.
Well, but even then, like if Moroccan caches the data for so long, like I mean, if it sees the query and says allows it.
So I think someone was cutting in and out.
Adam,
anyways,
can you try and asking that again?
I said I heard someone cutting in and out with a question, so I didn't hear the question.
It was Adam, and let's see if Adam can repeat his question. Adam, can you improve your mic and repeat, please? Okay, let's proceed, Alon.
Okay, so at a high level, the sampling error is dependent on the time of the incoming sync messages, because what we sometimes see is that you have cyclical behaviors of some of these local clocks, and so sampling just at the time the sync message is received may give a skewed view of the actual clock behavior. And the second downside is that a follower can report, because it does calculate itself, can report any value it wishes, including one that is not correct, either due to coding error or intentionally. And has also been pointed out, there are limitations to how this can be propagated. The egress method basically works on the opposite. It measures the time that a PTP message was transmitted from an egress port. Now, the egress method only cannot be used across either a TC or a BC, so it really needs to be worked on a directly connected device. But the idea here is, for example, a follower can report at time any event is sent out. So if the follower sends out a delay request, ignoring whether it would send it out, it can say the last delay request message I sent was at global PTP time X, as per my recovered clock. The advantage of the egress method is that the monitor evaluates the error. It doesn't rely on the follower to report it, and the reporting can be done in band with the proposed TLVs or using other methods, including signaling messages. And the time of the reporting is decoupled from the receive time of the incoming message. Now, as I said, the downside is that it needs support from directly connected device. One way of doing that is to actually implement this inside a switch that's directly connected to the dot. So potentially in today's disaggregated networks where we can add some additional software function to the switch, this is something that could potentially be added to the switch, but it's something that with a standard TC or BC cannot propagate a switch. Here's the TLV used for the egress monitor. So the idea here is that what we tell you is the event type that was used. For example, we monitored a delay request, or we monitored an announce, whatever message we monitored, and we tell you the timestamp that the PTP, the local PTP time at which that message was sent out in the event egress timestamp. Then the receiving side can see when it received that same message. It knows the receive time of that message, as well as have some reference to the reference time, and can measure difference. The problem is using the egress method is that often it's based on the transmission messages, like the delay requests or announce or p-delay requests, whatever message happens to be used. If those messages are sent immediately after sending a sync message, or immediately after, then they might not reveal the actual time error. And again, we've seen this through other devices where the egress method often tends to show a smaller error than we typically have, especially when you have a clock that is not synchronized very well or is not very stable. So I'm going to skip through this a little bit, and I'm going to go into the reverse sync. The concept is the reverse sync message. The follower sends its time to a monitor device using a PTP message. It is called a reverse sync, as in the original implementations, we actually used a sync message to send the time. And originally we could send it back on the same path, though really it could go on any path. And there are multiple implementations being used in the wild today, and we'll talk about them in a couple of the following slides. The current proposal, the 15 working group, is trying to standardize as an optional feature, and we're not actually using sync messages to it, rather we're defining a new signaling message to do this. And there are links here for those people who want to look at them. And if you're not a member of the 15 working group, you won't have access, but this is, or at least not a participant, but this is a good opportunity to get involved in 1588. Here's call to action. So there are a couple of existing implementations I'm going to just look at. One of them is the one that's defined by Avnu, and this was published, I think, about 6 years ago. So it's been up there for a while. And the idea is that the reverse sync is just sent on a different domain. So the forward sync is going on the standard domain, and we send back the reverse sync using a sync message on a different domain. There is a method for turning on or off the reverse sync in the follower, and then because it's just a standard sync message, a bridge, whether it be a TC or a BC, knows how to send it out. This assuming the bridge supports multiple domains, which in today's world there are many bridges that don't, but assuming you have a bridge that supports multiple PTP domains, it can do this. The monitor can also be a leader or the GM. It can be the same as the leader that sent the time, or it can be a different leader or GM. The measurement is initiated by the sync message. The measurement traffic is isolated using domains and special signaling messages, and the measurement protocol operates in 2 domains. And again, there is a link here to a public page where you can get information about this. Another existing implementation is from Meinberg, and this is
Alon, one question. This is Michel. What is the underlying reason why those reverse syncs are sent on a different domain?
It's to prevent confusion on the bridge, and to actually get the bridge to forward it. Typically, a bridge is going to use the best master clock algorithm to select within a given domain only a single best master clock, and it's only going to propagate that one. Now, if you have 2 sources in the same domain, it's gonna, number one is you don't want it to pick the one coming from the follower, but assuming the follower was smart enough and didn't send announce messages, so it's or send announce message indicating it's a really crappy clock, it wouldn't be picked. You still want the bridge to be able to propagate that and either acting as a transparent clock or a boundary clock and correct it. So putting it on a different domain allows us to do that. We can configure the switch to be able to propagate that, if that makes any sense.
Yeah, okay. Now, how is this different? Let's say everything is operating in unicast. Is there a need to do
in unicast, you don't have to use a different domain. In the Avnu implementation was focused on GPTP, which uses multicast. So that's why there's a different domain. So I should have led with that. So because the Avnu implementation was focused on GPTP, which is always multicast, a different domain was used.
Okay, that I think I can
that
see.
Makes sense. In unicast, you don't have to worry about, you would not have to worry about domains.
Yeah. Okay. Thank you.
No problem. Okay. Then Meinberg is using a different approach, which is the netting. What they're adding an additional TLV to the delay request. This TLV causes the monitor device to not only respond to the delay request by sending a delay response, but also sending an additional sync message and follow up with the time. Now, essentially, what this letter is that the delay response is going to give the T1 and T2 times, and then the sync and follow-up will provide the T3 and the T4, and the TLV will carry the PTP time of the T2 message. And this gives essentially the complete information that's needed. Then these are the two that have been publicly documented. There are other reverse sync methods that are in use that aren't documented, but these ones at least are available for reference. So when looking at 1588, we discussed some of the desired properties. So the first property we want is we want the measurement to be initiated by the monitoring node. We don't want the PTP to continuously send the reverse sync, because that can go haywire and you can have a lot of devices sending a lot of traffic. The idea is we'd rather do this as a request from the monitor node. So the monitor node says, hey, please give me your time, and the follow node responds to that. So then the second is we want the measurement to be independently executed, i.e. we don't want to schedule the measurement. And this gives the ability to not require any state on the follower, and also not to depend on any specific time of the measurements. The reverse PTP exchange could be significantly less frequent, and that's typically the case in typical PTP messages, but we can increase the measurement interval if we see problems. So typically we might measure this, maybe once a minute under normal operating conditions, but if we see something that's wrong, we might start and measure this 32 times a second to see what's going wrong. The measurement times should occur at the different fraction of the sync interval, so that to avoid sampling time artifacts. So we don't want this to be, synchronous with the sync interval. And to detect network asymmetry, we recommend having the monitor on a different PTP communication path than the GM, or potentially having multiple monitors on different paths to measure this from different perspectives. This is the picture of the proposal in the current 1588 that's being discussed in the management group. And you can see we're showing you got a GM that's somewhere on the network, you got a PTP instance somewhere else on the network, you got a monitor that's somewhere else. In the case of a typical data center network, it's fairly easy to implement. One way of doing it is to potentially have every PTP instance get its time from one set of GMs, and then even potentially have a different set of GMs act as monitors for those instances. And there's many different ways to instantiate this. Again, this is of course showing a ring topology, not a typical clause structure as you would have in a data center, but the concept's the same. The proposed message sequence is that using signaling messages, the measure request is a new message. Instead of using a sync message, we define a new message so as not to interfere with a sync. It's using the same domain number as the measure domain. This allows us to behave in the same way, both whether we're using unicast or multicast. And the measure request event and response are both unicast event messages, even when operating in a multicast environment. And this and the unicast follow-up is a unicast general message. It's not an event message. And how BCs and TCs can help. BCs, if they support this, can correct the measurement request event and the measure response messages for the dwell time by updating a correction field just like they do in other messages. So the concept is we're creating something that's similar to a sync message, but is specifically designed to measure this. It's always unicast. The reason we chose unicast is it allows us to put the monitor anywhere in the system, and it gives more flexibility. In the case of working in a PTP, we still use signaling messages. The measure request is unique. We still use the same domain number, and the measurement request is always unicast, but the response can be either unicast or multicast depending on the implementation. The measurement response follow-up can also be a unicast or multicast, same as the measurement response. But again, the monitor can be anywhere on the network. And again, the BCs in this case measure the dwell time and the upstream link, just like they do when we use, similar to what happens when the P delay correction is done. What are these TLVs that we've defined? The measurement TLV, and the padding is equal to the measurement response message length. We want them to be the same. The response and this, the measurement request is very similar to a sync message. The measurement response TLV contains the measure receipt timestamp as well as the measurement response timestamp, and the measurement response follow-up message contains the measurement receipt timestamps and the precise measure response timestamp. Again, if two steps is used, right? If one step is used, this information is the measurement response TLV. We can adjust the reverse sync rate for better sampling, so you can do the reverse sync in a rate that's different than the sync message, and it can be any rate. Again, typically you're going to do it at a rate that's significantly slower than the sync, but you can do it at any rate you want. And this doesn't apply to data centers, but there is an advantage to using reverse sync for integrated devices. Integrated devices that have a follower and a bridge internally and don't expose the connections between them. And the advantage is that a reverse sync can traverse the bridge, and the implementation is relatively straightforward. It can be done using existing sensing code, and that's my conclusion. I've used up most of the time here, but at a high level, this 1588 is defining not only how to synchronize time, but traditionally it didn't define how to validate time, but that's changing, and 1588 is providing some tools that can help. Without monitoring, time sync errors can go undetected, and there are many options available as we've discussed here. And standardizing the approach, regardless of what approach you use, doesn't matter whether it's measured within the device using peers, using monitors, but having something that's standardized will help improve the adoption and reduce monitoring costs. And so finally, my call to action here is participate in 1588 and other standards groups, and either support these ideas or come up with your own ideas and pitch them. And finally, I'm going to pitch that that testability and monitoring should be considered as a future track for OCP TAP. I think this is an area where there's a lot of potential ideas or questions. I think it'll be good. We don't want to slow down anything that's happening now, but I think it'll be great for a OCP to work on this and to see how we can improve the ecosystem here. That's it. Any questions? And I'm gonna stop sharing so that I can, or at least see if I can read the chat window.
Alon, I have a question. With regards to the servo, do you think like there is room to have, let's say, something based on Kalman filter, or like when
Absolutely.
when we have like the loss of like the sync messages, usually the divergence right now, when you look at, let's say, for example, the existing implementations, the divergence you get, it's definitely much higher than what you expect, let's say, from a holdover. Like, so
yeah, it can be, yes. And yeah, there are absolute things that we can do again on the node itself to measure its behavior, including potentially using different types of filters or analysis and to really look for what I'll call them different phenomena.
what do you think? What do you think? Let's say, since the PTP4L implementation is basically based on state machine, like the architecture of it, what do you think? Like, if we have like an S3 that is detected when you have, like, when you enter holdover, that will basically imply it's like it's different coefficients or something. Like, basically, it looks for a window of like what were the coefficients, the corrections, the PPB corrections, and he applies that. Like, what do you think of that? Wouldn't that be a good approach?
I think that's a reasonable approach, and I would love to prototype that and try that out. Right? It's a lot of these things are great ideas, and we have to kind of do up some POCs and also think about what the potential holds.
Yeah, because right now you can see like S1, S2, like S0, S1, S2, and then S2, and then holdover, still S2. You're stuck with the last correction and fly.
Yeah, and there are different approaches that are used. I mean, in many cases, holdover is not based on your last reading, but there are many implementations where the holdover is based on a much longer average or a much longer reading than just the last reading. But that's not. I don't believe that's how PTP4L is implemented.
Yeah, no, PTP4L I don't think has any mitigation for that. So I think a good way to basically have it non-disruptive and backward compatible, let's say, change on PTP4L is perhaps in the profile. And I don't know, Michelle, you're here, right? So is there anything, let's say, in the profile that dictates, let's say, how many packet losses you're considered now entering, let's say, holdover? And then once you enter holdover, you have like an entire different, like, let's say, mechanism, how you're going to deal with things based on the past. So then based on the past means you have to always prepare for it. So something like this perhaps will be non-disruptive and backward compatible. Like, Michelle,
you're on mute.
Yeah, sorry, Ahmad. Yeah.
Is there anything in the profile that dictates how many packet losses, consecutive packet losses, will determine you're entering, let's say, holdover?
Not specifically, no. We have in the profile today the typical timers like announce receipt timeout. That allows you, that allows you to switch over to another GM if there is another GM, and if there is no other GM, then you go into free running or holdover.
Okay.
So as long as
but
there is a
that one is not the state machine of the servo.
Because not of the servo,
that
but it's the state machine of PTP.
Okay.
Yeah.
Yeah, maybe we can like we are actually thinking, Alon, about, let's say, an entire new work stream for the servos.
Makes sense.
And if you're interested, I don't know, we had some more interest from some other people here. Like if you're interested, we can talk more, and then we can perhaps see who else is interested to get that rolling, because I think it's needed, really needed, to have something like, let's say, I don't know, a complement. I don't want to fork and then just go separate. A complement to what we have with PTP4L, have it backward compatible, but just with more features and richer. And then once done, we can actually reach to Richard and see if he's okay putting it back, let's say, on PTP4L.
Or better yet, work with him ahead of time and get his help.
Yeah, absolutely. Yeah. Okay, any questions before we wrap up for today? Elad, anything you want to add?
So thanks, Alon. That's been great. Very.
Okay, thank you. Thanks for having me.
Awesome. Okay, thank you, everyone.
Thank you. Bye-bye.
Thanks.